Okay, so let me start by saying I'm very grateful to the organizers for organizing this. So Keith, Andrew, and Maciek. It's a very nice occasion to have some nice memories of Konrad. Thank you very much. Well, I will talk a little bit about science, not too much, but what Konrad was a scientist. That was a great part of his life. So I will say a little bit about this. And does this work? No, it doesn't. Oh, it will if I put this in.
This is for fun.
You sure?
Try it.
Well, they say electrical appliances work much better when connected.
Yeah.
I heard that, but I forgot. So,
Not
I don't think, no, it doesn't. Anyway, so it doesn't matter.
Well, this
I
one.
do it like that. So that's a photo from. It was mentioned that I was the first PhD student of Konrad. So that is that occasion when I was granted the PhD degree at the University of Warsaw. So that's a photo of us together. That was 2007. And actually, I'm starting to discover new things. I think this is not on. Laser is not working. So what do I do?
Switch it on.
There is an old-fashioned stick just.
Old-fashioned stick. Where is the old-fashioned
It's just
stick?
next to the blackboard. On the other side.
Thank you. That's better. Okay.
You can use this. This is mine. Just press.
Able to
Press.
Okay. Thank you.
able
So,
to.
okay, so this is, well, Konrad, as Maciek has said, Konrad was a wonderful supervisor. He took really great care of me. And I owe to Konrad a lot. So I mentioned here few research visits that I have made and that I owe to Konrad. And those were rather substantial visits for me. So the first one was in Grenoble. I was a Socrates Erasmus exchange student, but Konrad took part in arranging that for me. That was 2002. And that was a visit to Grenoble. I actually took part in an experiment on rotating liquid and connecting some wires to put the magnetic field on. It was quite interesting. I wasn't very much interested in the experiment, but actually the topic of my master thesis emerged from that visit. So that was nice, and I met a lot of people. So that was one nice. Then I visited Andrew Gilbert in Exeter for a month. That was a British-Polish young scientist program. And well, there is a story connected with that, a short story that I applied for this, but I actually didn't get it. So I was unlucky. But apparently Konrad went to a meeting at the embassy. He met the guy who actually organizes the program. And he said, well, my PhD student didn't get it. Oh, really? Okay, he will get it. So I got it. And that's how I went to Exeter, which was nice. And then also there was this David Clayton Fellowship, which I owe both to Keith and Konrad. I visited Keith for 3 months in Cambridge here. It actually turned out to be quite beneficial. I worked very hard, and there were some things that emerged, and later we published that with Keith and Konrad. And a postdoc at the Department of Applied Maths in Leeds. So that was 3.5 years. So all those 4 visits, I very much owe to Konrad, and that's something I think was substantial for me. I'd like to also mention some side activity that I was encouraged to do by Konrad. So the first one here is when I was starting my PhD studies. I don't even know how, but Konrad met people from the Polish Forestry Commission, and they asked him to do some statistical analysis of forest pests.
That's very relevant now.
So he went to me and he said, well, maybe you could do some statistical analysis. I said, all right. I mean, they were paying for that. So we were happy. And so we did that. We went to that forestry commission. We talked to them. Actually, we learned a little bit from those people, apparently, about, I don't know the English word for that, but when you take a stick and you look for water.
Divination.
Sorry?
Divination.
Divination? Okay, so we learned about that as well. That was quite funny, and of course, was a reason for a lot of jokes as well. And another one was with Mark, who is here. It was about some numerical analysis of urea filters. It didn't go very far. We didn't get a grant for this. We applied for a grant, but we've done some analysis with the numerical package fluent that I was learning at that time. It actually was promising, but then we somehow dropped it. So the first paper we wrote together with Konrad was in physics of the Earth and planetary interiors. That was about an interesting effect of superrotating or superspeeding jets caused by magnetohydrodynamic effects. And here's the problem. So there are actually two geometries that we are considering. One is spherical, and the reason for considering the spherical geometry was that it was supposed to mimic somehow the situation in the Earth's core. So that would be the inner core of the Earth. That would be the outer core, filled with liquid iron, and then the outer shell would be the mountain. Okay, so rocks, basically. Now, a flat analog of that system is here. Now, the main point in here is that the dipolar field in this geometry has a specific line which touches the outer shell at one point. Okay, so that's the tangent line in here. So in the flat geometry, we have the magnetic field in this form, and it also possesses that critical field line which only touches in one point the top boundary. So why is this problem interesting? So we drive the flow by moving that bottom boundary that way. So here is side view, and we can see that we're moving that boundary, but that one is at rest. Now these are the field lines. Okay? So what is happening really is that an arcade of field lines forms which do not touch the outer boundary at all, and they just move along with that bottom boundary, which is conducting. And they just move along with that boundary, and they drag the fluid with it if the magnetic field is strong. So inside that arcade, the fluid moves at the same speed as the bottom boundary, whereas outside this arcade, it doesn't have. So these are the results. And yes, so these are the numerical results for this problem. And you can see that this is the bottom boundary, here is the bottom boundary, here is the top boundary, and this is the velocity field. Okay? What is actually happening is that inside that arcade, so in this region here, the fluid is moving at velocity u0, so that same velocity as the bottom boundary. But along that critical line, the fluid actually is speeding with greater velocity than the bottom boundary, which drives the whole thing. And close to the top boundary, it's moving at a high speed. So that was an interesting effect. The reason for that is that when you look here, here's a color map of the velocity field, and the lines here show you the flow of a current. So you can see that the current enters the top boundary, it also enters the boundary layers. But the point is that if you recall the magnetic field line, which went like that in here, right? Basically what the gray color shows here, dark gray color, the magnetic field at this point is perpendicular to the current, and that causes large Lorentz force, which accelerates the flow. And that's the effect we are studying. That's the super speeding jet that forms close to the outer boundary. And what we are mostly interested in was the influence of conductivity of the outer boundary on this super speeding jet, on the value of the velocity in that point. So that was quite nice, quite nice analysis. And as I said, this was my first paper with Konrad. For me, that was my first paper at all. And there were also other 6 papers that we did with Konrad. I mean, at some point of my PhD, I said to Konrad that it's enough of super speeding jets. we've done that. Can you think of something else for me? So he said, well, there is a problem of elliptic instability. Maybe you would like to see how magnetic field and background rotation influence the elliptic instability. Elliptic instability meaning an instability of a vortex that is not axially symmetric. That's what matters really. It can be an elliptic vortex, for example. So we had a few papers on that. The most important papers being the JFM papers. So that's this one from 2009 and the paper with Keith in 2012. That was quite a nice experience because actually I think I asked Konrad for that problem in somewhere at the beginning of 2004. I started work on that. I found some solutions for the most unstable modes and how they are destabilized. So I was ready to basically write down my PhD by the end of 2004, more or less. And then we found a paper from summer 2004, which was written by Leibowitz and his Bible. And basically, they have solved everything that I was solving for during that year. So the only fortunate thing was that they didn't include background rotation. They had only magnetic field. So I've done that anyway. So we finished that, and we basically concentrated on the effect of rotation because of that. So here is why this is important at all. So this is a Keplerian disk, and if you have a Keplerian disk rotating that way, there are vortices that, well, more or less elliptical, counter-rotating, that form naturally in the Keplerian disk. And they influence the stability properties of such a disk. So to model that, we can come up with a very simple velocity field, which is linear in x and y, and it's depicted in here. Magnetic field is simply uniform and vertical, and the background rotation is also vertical. We use the rapid distortion theory to analyze this. So perturbations looks like this with k time dependent. The point is that the wave vector for those modes moves also along an ellipse, which is perpendicular to that ellipse. And theta is the angle between the axis of the magnetic field and the wave vector. That's the minimum angle in the motion. This is the visualization of the mode. So these are the streamlines. That's time equal to 0, the initial stage, and this is how it evolves down. So you can see that the evolution of streamlines is quite impressive. These are the magnetic field lines which seem to dance really during the evolution, and those are the current lines. Here what we have is some color maps of a growth rate. So what we have on one axis is that angle theta from here, and this axis gives you the angle theta, and this is the ellipticity. So I mean the point of this picture here is really just to say that there was really a large amount of regimes for that problem, and depending on the relative values of magnetic field and rotation, the system jumped into very different regimes, showing some different instability types which appear, for example, here for purely horizontal modes, let's say, and this instability, for example, is not present in here or over here. So that was an interesting topic. Now, one of the papers I have mentioned, that was the paper with Keith also, and that was the JFM paper from 2012. We have investigated the type of electromotive force that could be generated by the electric instability. So this is one of Konrad's main activities, NHD in general, and we were, we have come up with some expression When I first arrived at that expression, I was a little bit puzzled because, well, the details of the calculation involve Floquet theory. And, well, I found EMF in an ideal system without any diffusion. So at first I just thought that it's completely wrong, that I must have made a mistake. But then I realized what was going on. It was simply that the modes I was using to calculate the EMF are slightly different than in the standard situation, because in the Floquet theory, they are simply linear combinations of the standard modes. And apparently it turns out that if you take those linear combinations, you get an EMF, which is non-zero but oscillating in time. So that was an interesting result, and I'm still working on this, so that research is definitely continuing. And well, I have come up with some solutions at the moment. I'm quite happy with that. One of the papers is actually being reviewed by Keith at the moment. So there's an occasion to discuss. So if I manage to persuade Keith that it's all right, then I get a paper. We'll see. So and now those results were presented on conferences, but one of the very enjoyable conferences was the Bosman conference. We went to Yellowstone Park, here, and here, with Andrew Gifford, as you all recognize. And these two photos are from different parks. I don't even remember the names. We just took a car and we went traveling just to see something. I really enjoyed that picture. That's a very nice photograph. And we had a very nice time in Bosman. I must say this conference was organized for Steve Childress's 75th birthday, I think. And as I said, it was very enjoyable. There was also another conference in Cargés on Corsica. Oh, here's Kasia and Konrad. We had a nice dinner in a cafe and some views, as you can see. And also here's Keith, as you can see, what Konrad. Here, this is Lorette Tuckerman, Marie Farsh, and here David Gabbins. I think here is Axel Brandenburg. So, also had a lot of nice time in Cargés. Just to tell you how that research is continuing, as I said, this is the bit that is actually being reviewed by Keith at the moment. So it's this is the influence of.
He's giving me a very tough time.
It's an influence
Is the influence of viscosity on EMF generation in flows that are not driven, not forced. Right? And so, for example, if you say, imagine a galaxy that was forced billions of years ago, but now it's basically rotating because the dissipation is so small that the flow still exists, but it's not forced anymore, then you can sort of think of such a situation that what you really have there only is the eigenmodes of that system. And you can study the problem and, well, come up with that sort of an expression where we've got viscosity and resistivity, which in a sense compete with each other in the generation of the EMF. Of course, I mean, in that system, like if I mention galaxy, they don't really compete because typically in galaxies the viscosity is much, much greater than resistivity, so it's just that term that survives. Another thing is, there's another paper, and it's the thing that I was trying to explain previously. So when you take the EMF and you just do a standard calculation, but you, instead of just taking one mode, you take a combination of two, you get the standard contributions, right, from self-mode interactions. So U1 is interacting with U1 and U2 with U2, but the cross interactions, they give you a contribution as well. But that contribution is oscillatory impact. Okay? Now, whether it matters or not, it's an issue, and that has to be resolved. I'm pretty sure I know the answer at the moment, but this is, well, I sent it to a different paper, and apparently they didn't send it to Keith. And somebody else is reviewing that paper, but, well, I don't know. So let me end with that nice photograph. That's from Carl Schurz. And I think everyone is recognizable. And that's Marie Farge, for those of you who don't know. Well, and that's some guy who just fit in the photo. And, okay, so, thank you.
There are a few equations here. Anybody has a question? Maybe a reviewer of the paper. Many questions.
So better to move on.